go. Hello and welcome back to Calculus 1, section 3.1, Introduction to Derivatives. So what we have is, well, we have to go back in time first. Recall that there is something that it's called straight line, linear line, right? And this line can be perfectly described by 2 points, say x1, y1, and x2, y2. The formula would be y equal mx plus b. We call this slope-intercept form. And the slope m is y2 minus y1 over x2 minus x1. This is your algebra. So you can use the 2 points that are given to you to calculate the slope, and you can use one of the points with x and a y and that slope to find b, and that will give you the equation of this straight line. Now, if you have a function, say you have a function like that, whatever, f of x. It doesn't matter what you draw. So you have a function, and then you draw a line that cuts through the function. Again, there are 2 points of intersection, and then clearly this straight line is of the form y equal mx plus b, where you can use these 2 points, again, x1, y1, and x2, y2, to create this line. Now, this line will be called a secant line. From its Greek origin, it means to cut, right? So you would say that in this case, m secant is y2 minus y1 over x2 minus x1. So now we have this particular line. All right, great. So now we just, added the straight line to the function. That's the next step up. In pre-calculus, you learn that f of x is y, meaning that f of x1 will be y1 and f of x2 will be y2 as you plug these things in. So now you can rewrite the secant slope of the secant line as f of x1 minus f of x2 minus f of x1 divided by x2 minus x1. And actually I am going to box this, but I'm going to box it lightly because we're actually not going to use this concept in calculus. But I want to box this because this is this is a unity of many different concepts you learned before. Slope of the line. We talked about a secant line now because it can cut the function. You have the pre-calculus concept that y is f of x, so we replaced y's with f of x's. So entire slope of the secant line now can be computed in terms of x. You don't need the y's at all. So it's the most compact way, I would say, to compute the slope of the line in the pre-calculus era. And now we're opening doors to calculus. So calculus is the study of change. And we've seen in the limits, right, that we are allowing x to approach 3. So we don't say x equals 3, which was the reason why we do not calculate limit at 3. We calculate limit at all of the infinity of the points around 3, because we are approaching 3, right? We are marching towards 3. So that motion from calculus, right, the idea was x approaches 3, so there's the motion there, right, the approach. Now, we want to go further with these ideas, and I want to go and now have the same graph as before. Let's let's put this, doesn't matter what it is. It's just whatever it's easy to see. And now we're going to pick, let's say this is point P and point Q. I'm going to use the same letters that your book is using. And I want to put this point P at A, and I want to say that this point over here is fixed, okay? So that point is the fixed point. Fixed point doesn't move. And I'm going to draw a secant line through P and Q. I can't see this one very well, so let's put something darker. There we go. So this has the M secant, right? Now, we all know the way to compute this. You just have the coordinates for P, coordinates for Q, compute the slope using algebra, everyone is happy. Now we let calculus operate over here. What I'm going to do is I'm going to allow this point Q to travel along the function. So its value x, right? Its value x, it's going to start moving on the x-axis towards A as the point Q goes here, becomes Q prime, goes here, let's say, Q double prime. Obviously, it's going to strike every point along the way. I'm just going to put few of these. So Q prime, Q double prime, Q triple prime, right? It's just a progression in time. And it's going to hit every single point and eventually collide with P and become a single point right there. So now I can draw all of these lines, all of the secant lines that connect. So here is the next one, and the next one, the next one. And as you can see, it keeps, the slope of the line keeps changing as the point moves, which is common sense because every time the point Q moves, it has different coordinates, so the slope that I have up there boxed in green will have a different value because the numbers in the calculation are different. So as long as this Q is moving along the line, every time you take a snapshot and you want to check the slope will have a different value. And then eventually, point Q is going to collide with point P. And that is going to create an issue because both x values will have the same number. And what happens then? Dividing by 0. So I hope you see that as Q, I'm going to erase these lines, but it's good to have them for now. Let's use the happy colors. Right, so this one, right, and then there is the x, and then there is the x again, and you can see how these x values are marching, right, as the point is moving towards the left. You see that the x value is moving towards A. So it should be common sense that as soon as these 2 points collide, the x coordinates will be the same and you will not be able to compute tangent line. Sorry, you will not be able to compute the slope of the linear line. But the line exists because the progression of these lines is such that at this point, you are going to have what we call, it's a special line, we call it a tangent line. So over here at P, and I draw that red, there is still going to be a line. Now the issue is that algebra becomes useless to calculate that line because you only have one point. Technically what's happening, I'll draw another picture over here for these tangent lines. What happens is if you have a single point, right, there's only one line, we call it a tangent line, that passes through that point. And it's perpendicular to the curvature, right? So this little curve, think of the little neighborhood there, of the curve. It's a part of a circle, so maybe, you know, maybe the circle would look like that. So there will be a center of that circle somewhere for that little curvature, and then if you draw the radius from the center to the point, the tangent line is always perpendicular to that radius that you have. So there can only be one tangent line per point, per function. But you see how many blue secant lines you have? You have infinitely many, because the blue secant lines are going to go to every single other point, right, that you have, Q. But there's only one position, right, where when they collide into a single point, and then you can draw only one line, and it's called a tangent line. So now, how are we going to calculate the tangent line? And we are lucky to have the concept of the limit, because you see that x goes to a, right? So you can see that all of these blue lines go to the red line, and the red line is the limit of all of the blue lines. So one of the most important formulas we have in calculus is going to say that the slope of the tangent line is equal to the limit of the slope of the secant line as x goes to that a. Now that translates into limit f of x2 minus f of x1 over x2 minus x1. And this is a concept. We are not going to use this to compute anything. But this is the concept of what the slope of the tangent line is. You can't compute it using the algebra, clearly, because x1 and x2 end up being, well, this is actually x1 going to x2 in the way I wrote it. So now, I would like to figure out the way to compute this. And this is where you guess we are going to convert this somehow into the difference quotient, and we will be using difference quotient to compute these things rather than anything else. And again, it's just 2.3 mechanics. So we're not learning new methods of computing or new types of problems today. This is highly conceptual lecture in terms of theory, right? And then you have just the mechanics of 2.3 to compute stuff. So where do we start? We start by understanding that our m secant, looking at the picture up there, is going to be f of x minus f of a divided by x minus a, because I have a point, right? A is my x1, y1, right? And then where x is, that's like x2. So you have a point P, which is a f of a. So point P is a f of a as your x and a y. And Q is just x f of x in our case. So we're just using the secant slope. So y2 minus y1, so f of x minus f of a, divided by x2 minus x1, which is x minus a, in our notation now. So we just changed names, nothing special. And looking at the red definition up there, m tangent then is the limit as x goes to a of f of x minus f of a over x minus a. So this is our definition for the tangent line. And we see it from the picture, it has to be that. So now, all I need to do is to figure out the way to make this more user-friendly. And we get that by simply defining some age as x minus a. As soon as you, so I'm just going to say here, let age be x minus a. Now, you know, in honors section of the calculus, students actually have to learn this derivation, because it could be a question and it's needed later for Calc 3 and everything else. In your case, you need to know how to do the problems, which are technically 2.3. But there is a cool thing about all of this here. So now when I have that age is equal to x minus a, I can just simply replace all of these things here to eliminate all of the a's. So what I can do is I subtract a on both sides over here. X minus a clearly is going to be age. And then over here I can solve for x as, sorry, I'm not eliminating a's, I'm eliminating x's, sorry. So age is going to be, x is going to be age plus a, or a plus age. So now I have new formula for m tangent, limit x minus a on the left for the limit, well, that's age, goes to a minus a is 0. See that we are forming the difference quotient slowly. On the right hand side, f of x, well, x is a plus age, all right, minus f of a stays, divided by x minus a, that's age. This formula here is slope of the tangent line. And this is already useful to us. We can use it to calculate slope of the tangent line. So this formula is the slope of the tangent line. Now, what am I going to do with this computer problem? Find the slope of the tangent line for f of x equal x squared minus 3 at x equals to 4. All right, perfect. We know that, you know what, I'm going to actually add something here in red. So slope of the tangent line at x equals a, okay? Because it's a specific location, and that's why we call it a, right? It's a specific location on x-axis. That's a key point, because guys, what I just added, everyone, eyes on the screen, what I just added here tells me that a is 4. I understand that it says x equals 4. It is supposed to say x equals a, but I put 4, which means a is 4. That is the location at which we are looking for a tangent line. It's very important for you to connect these two as soon as possible. So x equals a, meaning a is the location when we are looking for the tangent line. So now from there, I know that a is 4, which is what I'm going to be plugging into the equation up there. All right, what's m tangent? Well, I need to create this piece f of a plus age. Great. So I have f of x is equal to x squared minus 3, and I have f of a plus age then to be a plus age squared minus 3. Welcome function composition, right? Where we replace x with whatever we need to replace it with. In this case, it's a plus age, because that's what we need as a piece to plug everything there. So now what I have when I expand this is I have a squared plus 2ah plus age squared minus 3. And finally, we know that a is equal to 4, so I can have f of 4 plus age, and that's going to be 4 squared plus 2 times 4 times age plus age squared minus 3. Compute everything here. That's 16 plus 8 age plus age squared minus 3 to give us, put it in order, age squared plus 8 age and then plus 13. So the first piece of the puzzle, which is this piece over here, is this. We build it up from function. We replace x by a plus h. We expand all the algebra. Then we say, what's my a? I'm looking at the point x is 4, which is a is 4. So plug in 4 for a, expand that, compute, and we have our first piece of a puzzle. That goes in a difference quotient. Now we also have f of a. Well, that's not a problem, right? Because f of a is just f of 4. So compute f of 4, which is 4 squared minus 3. That's 16 minus 3 is 13. Great. So I need this result here, and I need this result here. They go into the formula. So now let's just compute the formula. Slope of the tangent line is equal to limit, age goes to 0, and now on this line I have f of a plus age, right, which is age squared plus, you know what, let me write it one more time, formula. So it's f of a plus age minus f of a divided by age, and now in the next line I'm going to substitute everything so it's clear. F of a plus age is age squared plus 8 age plus 13 minus f of a, which is just 13, divided by age. These guys cancel. You see that in the next step we can factor out age, leaving us with age plus 8 divided by another age. These guys now cancel. When age goes to 0, the answer is 8. So slope of the tangent line is equal to 8. And that's the answer. So what we did in this particular problem is we found the slope of the tangent line, and we are provided with only one point. Come on, get excited. Holy nightmare, your whole life you've been looking for slope of the line having 2 points, right? Really? I waited a week to bring you this news. That you can find the tangent line, that you can find the slope of the linear line having 1 point, and you're just like, okay, fine.
Brilliant.
Thank you. That's +5 on the next test for you, and then just -15 for everyone else. Just like, oh, it's calculus. Yeah, this is how cool life is now. So next time someone tells you, what do you know, right? Or they tell you what's new. Woo, I can now find the slope of the line with 1 point only. What do you know? Right? It's a good one, especially when they say, "Wow, what do you know? I have kids." Oh, really? Nice. Oh, I said fine at 4. I didn't want a 4. I wanted 6. Oh well, from scratch. Same function, right? F of x equals x squared minus 3, but x equals 6. What's the tangent line? What do we do? Everything from scratch, obviously, right? I'm just going to save a little bit on steps. Instead of computing f of a and then plugging in 6, I'm just going to compute f of 6 plus age. That's faster. So I have 6 plus age squared minus 3. That's going to be 36 minus 12 age plus age squared minus 3. So the whole thing, f of 6 plus age, is equal to age squared. What?
Wouldn't it be plus 12 age?
Yes, it is. I just, you noticed me like stop, right? Because that's not supposed to be minus there. So it is age squared, 12 age, and then plus 33. Great. Now I also need f of 6, which is 36 minus 3, which is 33. Great. And now my limit, m tangent is limit age goes to 0 of f of 6 plus age minus f of 6 over age. And we just need to plug everything in now. That's going to be age squared plus 12 age plus 33 minus 33 divided by age. Well, these die, right? And I can again factor out age. That's age plus 12 divided by age. These guys cancel. And I have age is 0, and I get 12. Great. Slope is 12. Same function, but at a different location has a different slope. Which should make sense that if I have a function looking like this, if I am here, tangent line should look like this, and if I'm here, tangent line is going to look like that. Those are different locations. They have different slopes, so the lines are slanted differently, right? All of these things should make sense. Except I just realized that I didn't want a 6, I actually wanted a -5. So we have the same function f of x equals x squared minus 3, and now we're looking for a tangent line in -5. And pretty much I'm sure, just because I'm me, when I'm done with that, I want to know what's happening at 107. And so on. Every time you change a location, it changes the slope of the tangent line. The calculation remains exactly the same. The result changes, and giving us a different slope. So you keep changing this. You have to recompute the whole thing from scratch, because this number changes, this function here changes. And that's the problem. This is highly inefficient, right? So what do you do as a lazy mathematician? You devise a way to solve for all of these in one shot, and then hopefully just plug in whatever number you get here. Wouldn't that be cool? That you can skip all of this work, right? You do it only once, and then no matter what number is provided to you, you can just plug it in and get the answer. That will be much more efficient than recomputing the entire problem every time you change the location. You've seen we have to do it, right? Recompute. So, all right. Yeah, but no. Right, I'm just going to put this over here, and then you will eventually go home, and you know what that is, right? So, what am I going to do instead? We have this amazing concept, and I just want to make this even better. And the way I do that is I say, you know what? Instead of having A plus age, that A being a specific location on x-axis, let me put x, which is any location on x-axis. Who cares, right? We don't have to marry it to a single variable, right? So a single location. We can just do for all locations. And then whatever value comes along, just plug it in. So this is what we are going to do in our next step. Our good old M tangent formula, which was limit h goes to 0 of f of a plus h minus f of a over h, we are going to just simply replace a's with x's, giving us M tangent to be limit h goes to 0 f of x plus h minus f of x over h, and now we can compute everything. I'm going to box this obviously with red because it's good, it's important, well, solid. Great. So now I have this concept. Let me try my previous problem of f of x being x cubed squared minus 3. And now I am not specifying any value here. I'm going to deal with that later. We can say x equals 4, x equals 6, x equals -5, right? All of them. So what am I going to do? I'm going to ignore this piece, right, at first. So I'm going to ignore this, and I'm just going to compute the tangent line, so M tangent, as the limit x goes to h of f of x plus h minus f of x over h. Okay, function composition. F of x plus h is going to be x plus h squared minus 3. Again, you're taking this thing and you're replacing it what? Right, just look at these four, right? So if it's x, it's x. If it's x plus h, it's x plus h. The shape of the function remains the same. So what am I going to, well, now expand, right? It's going to be x squared plus 2xh plus h squared minus 3. Ooh, look at this one. That's already f of x as is. I don't have to do anything for that one. So we just plug stuff in. M tangent is limit h goes to 0. We have x squared plus 2xh plus h squared minus 3 minus, and in parentheses, x squared minus 3. That's minus f of x. Cool. Limit h goes to 0. Get rid of parentheses. X squared plus 2xh plus h squared minus 3 minus x squared plus 3 over h. Whole bunch of stuff dies over here. X squared, 3 and 3. And we are left with terms that have h only. Now that's your checkpoint actually. Once you're done with calculation, if all terms contain h, you're pretty much good. Right? So I can kick h out, and it's left with 2x plus h. There is h in the denominator which dies, and you are left with the limit of 2x plus h. What happens as h goes to 0? Yep, so the answer is 2x. What you got is that the slope of the tangent line is 2x. That's what you have. Hey, x equals to 4 gives you the slope of 8. Remember what I had earlier? And if x was 6, the slope was 12. We have those calculations. Now if I come up with a -5, it's -10. Remember how I also wanted 107 in the next time around, right? Slope is 214. We found a function which generates all the slopes. You give me x, I immediately give you the slope back. Right? Talk about efficiency. You compute it once. No matter what point you come up with, you immediately have the slope of the tangent line. You know what the name of this function is? The derivative. So what is the derivative? It is a function that can generate any slope of the tangent line. Like this. You have a function and you have the derivative of that function. The sole purpose of that derivative is to tell you what the slope of the tangent line is at that point. Now you might say, well, okay, fine, I have a slope of the tangent line. Big deal. It's a huge deal. That slope of the tangent line measures the change at that point. All right? Try to walk up this wall like Spider-Man does. Go on. What do you know? You know you can't do it, right? What's the slope of that vertical line? It's infinite, right? You see that we are the concept. So you have something like this, which is a hill. All of us can hike this part over here. It's nice, right? And then some of us are going to have a very tough time going uphill right there. You know what the difference is between these two locations? Just the slope of the tangent line at every point. It tells you that. It tells you the steepness if you want to consider a function that shows, right, the steepness as you are hiking up the mountain or a hill or whatever. Maybe you have to drive up to those slopes off-road vehicles like military stuff and so on. Is it going to make it? A truck driver has to worry about the slope of the road because the cargo. Why is it called cargo? It's not on a car. It's on a truck. It should be truck go. If it's not tied, right, it might fall out, right? So there are a lot of things that this measures. Now it measures the change in that instant, and we are going to beat this concept to death for 2 chapters, so it will be clear. It doesn't have to be clear today. It's mechanics day today, right? When you're doing the limit from 2.3, that's it. But what we just did is we created this function, and now this function over here is called the derivative. And what it does is it computes all possible tangent line slopes. The next theoretical concept here, tangent line slopes measure the change at a point. They measure a change at the point. We are going to have a business application here, which is going to eventually, not today, which will show the difference between marginal cost and which is the derivative, and the average cost to produce something. And obviously, if you want to be any good in business ever, right, and maybe even do what Musk is doing, because he didn't start when he was negative 30 years old, you all have chance to repeat whatever he does and do more. He understands those concepts. Yes, he's an engineer and everything else, but he understands the difference between marginal cost, which is the derivative, and the average cost, which is the secant one, to create all the businesses that he runs. So we are going to explore the theory behind this in depth. What has happened today? We started with a concept from algebra that there are two points in space connected with a 2 points in space connected with a line, and you can use your algebra formula for slope. I'll put this gray box over here, which you can later upgrade into the green formula just by replacing y's with f of x's, which we eventually upgrade into the slope of the tangent line when we add the limit, because we can't compute slope with only 1 point using algebra way, but we can compute the slope with 1 point if we have the limit concept, and we do have it, so we use it, and we create this. And then we start computing slopes one by one, and it's labor, and it's long, and it's painful. And then we realize that we can replace the a from the formula with x, a being particular location on x-axis, and x being any location on x-axis, to create this formula. And then we don't care about particular locations anymore. We compute what we call the derivative, and once we have the derivative, that is when all of the different locations that you want to test come in to give you the slopes of tangent lines that you need to measure. So now, if I am thinking about spread of infectious disease or spread of flu or computer virus or whatever of that sort, I can say in hour 4 after the initial outbreak, we have it's changing at the rate of 8 patients per hour, 8 new cases per hour. In the hour 6, I have 12 new patients per hour. Forget about a negative. At hour 107, we are adding 214 new cases of flu or infected computers or whatever you are thinking about in terms of measuring the change. So that is what this thing does for us. So finally, we get to write the final formula for the day, which is the derivative, which is f prime of x, is equal to the limit of f of x plus age minus f of x over age as age goes to 0. And that is the formula that you use. That is the derivation from all the way from algebra back into Calculus 1 to define one of the most important concepts that humans ever came up with. So this is what Newton and Leibniz, now not in this form because they didn't have limit at their time. The limit was finalized about 150 years after the definition, but they were able to operate with these concepts even without the limit. So their definitions look different, but they worked, obviously. So now let's do a spicier example. What is the derivative of f of x equals square root of x? You go, oh, I know. F prime of x is the limit of f of x plus age minus f of x divided by age, right, as age goes to 0, and you just compile the difference quotient. So f of x plus age is going to be the square root of x plus age, because if f of x is root x, f of x plus age better be root of x plus age. And now we need to plug all of this into the limit. Do not forget to write limit in every step. It's like -2 per step, and if the problem is, 6 points and you forgot limit 4 times, you technically have -2 for that problem. So, wow, no one is complaining? Tough crowd, nice, I like it. So square root of x plus h minus root x over h. All I did is I replaced the pieces where they belong. So I know that f of x is root x. Right? So just plug in. We have to rationalize. So it's square root of x plus h plus root x divided by root x plus h plus root x. And that is now the limit. H goes to 0. When you multiply these, we get root x plus h times root x plus h is just x plus h. And then minus, the cross terms will cancel. Guys, what I'm using here to calculate this quickly is a minus b times a plus b is a minus b, a squared minus b squared, right? So technically, if you take a look at the first term here, which is a minus b, which is this puppy, right? And you look at the last term, it's actually this term here, but each term squared. So just look for the one with the negative sign and square each one of the terms. So I just get this divided by, and this don't FOIL it, just leave it in factored form, because remember, you're looking to cancel this h, which you will be able to do in the next step because x's die. And don't forget the limit. Now you have h over h square root of x plus h plus root x, and then these guys cancel, and you finally have just the limit h goes to 0 of 1 over square root of x plus h plus root x. Well, when h is equal to 0, what you have is 1 over 2 root x. This is known as the derivative of the function. So if the function f of x is square root of x, the derivative, you have this prime, the derivative of f of x is 1 over 2 root x. Now if I want the slope of tangent line computed at x equals to, let's say, 3, I know it's 1 over 2 root 3. Then you rationalize and whatever, right? But the idea is that you can quickly compute any tangent line slope by quickly now plugging in, right, x's into the formula and computing these things. Say something, Pete. It's like one of the most important lectures of your life. You signed up for Calc1, right? And also it's Saturday. Come on, it's weekend. Where's the holiday? Not holiday spirit, the weekend spirit, right? You all love this stuff. Yeah. Good morning. All right, so try one more example, and then transition into the lab, and then after the lab, we'll have a detailed review. Are you still offering the morning SI next week? Oh, Honors College is going to DC. Yeah. I'll ask Kevin. Okay. He might be.
Yeah, and I think we some nice stuff.
Okay. So we'll try to have another 7:30 SI session before the test on Saturday. Do you have still that Thursday at 12? Okay. So Thursday 12 SI is still on. So Thursday 12, I have 5 hours of office hours, so you are welcome to stop by. You don't need to email me or anything, just come in. And you have SI on Thursday, you have my office hours, and you will have a session now, and then we'll have the review, plus all the notes and lectures and videos and other things. Like, you really need to want to do bad I think. I'll look at it that way. All right, so an example that you should try to compute this, again, I can wrap this in 2.3 question, which is find the limit, right, of for the difference quotient when the function is 1 over x, right? So that could be, that is definitely something that you guys must know. I'm coming back, so I'm not taking any of the stuff with me, just my jacket. Write this stuff down. I'm just going to shut it off so it's not overheating, and I'm going to shut the projector as well so it's not burning the lamp for no reason. And